Eyal Cornfeld, which is local, and he will speak about currents in 1D fractional quantum world.
Hello, everyone. I'm Eyal Cornfeld from Tel Aviv University, and I'm going to talk to you today about work that I've done with my advisor, also from Tel Aviv, around Sela, that you've heard yesterday, that has just been recently published in PRB. And I'm going to speak about chiral currents in one-dimensional fractional quantum Hall states. Because I only have 15 minutes, then I'll just flash at the end our ongoing work with Luca Taglio, Marcello Strinati, Leonardo Mazza, and Rosario Fazio from Pisa and Paris. So just to give you a brief introduction of what I'm going to do, I'm going to introduce the fractional quantum Hall states and our system. I'm going to speak about our one-dimensional system, which is a system of two-leg ladders. And then I'm going to talk about the chiral currents that can be measured within those fractional ladders. So what I want you to take when coming to hearing this lecture from the fractional quantum Hall effect, the normal two-dimensional fractional quantum Hall effect, is the fact that we have a conductance that enable us to probe or to serve as a tool in which we can notice that we are within the fractional quantum Hall state. So the fractional quantum Hall state, which is very interesting, can be attributed to this fractional conductance, and it can serve as a probe to measure or to verify that we are within this phase. And the question is, first of all, can we realize similar phases not in two-dimensional systems, but in one-dimensional systems? And what physical observables should be measured in order to realize that we are in that state? And let me give you a spoiler, that would be a chiral current. So, okay. So why look at ladders at all? So our one-dimensional system is a system of a two-leg ladder. This is the minimal one-dimensional system that is affected by magnetic fluxes. We can have inserting a magnetic flux here, whereby a particle that's going around one flux in the ladder would feel that magnetic flux. Moreover, there has recently been experiments where those ladders had been created in cold atom systems with a synthetic magnetic field, and this opens a new horizon of taking ladders of bosonic atoms and trying to create bosonic fractional quantum Hall states, which we can do in electronic systems. And moreover, a system of coupled two-leg ladders can serve as a microscopic model, the lattice model for modeling experiments in semiconductors of coupled wires. So let's look at the basic of ladder. So once we have a ladder, if we have an interchain hopping, we get a parabolic dispersion. And once we're adding some interchain coupling and a magnetic field, what we see is that we just for nothing get very simply an equivalent of a one-dimensional integer n equal to 1 quantum Hall effect, whereby if we tune our chemical potential to be in the gap opened by the magnetic field, we see that we have an equivalence of the n equal 1 quantum Hall effect, where we have a gap in the middle and a chiral edges at the end, and those edges have a current that's circulating around that sample in this simple non-interacting integer phase. And the question is, by adding interactions to this ladder, can we transition to other interesting fractional phases? And so the answer is yes. But before I do that, let's see that we can say not just fractional phases, but other phases as well. So in this experiment that I've talked about before, that happened by the Block group in 2014, what they've done is they took this system of a ladder and they've added a synthetic magnetic flux. And what they were able to see is they could get a phase transition between a Meissner and a vortex lattice phase that's very similar to what happens in type 2 superconductors. And what they've done to probe that phase is to measure exactly the circulating chiral current in their two-leg ladders. And the question is, are there other mainly fractional phases that we can achieve by once we've had interaction to those two-leg ladders? So how to generate fractional interactions? What we're doing is following the analysis of TO and K in 2014. And we're doing a perturbative approach of the coupling between the legs of the ladder. And in one dimension, what we get is a Latinger liquid, and the one-dimensional fractional phase is determined by the Latinger parameters and by the scaling dimension of our fractional operators. And what we do is we've seen that once you add strong interactions to the ladder, if you add, it's enough to have on-site interactions, whereby by mapping it to a Hubbard model, we can see that the just strong on-site interactions are enough to stabilize the bosonic n equal 1/2 fractional phase in that ladder. And this is a very important thing to notice, is that on-site interactions are enough to stabilize the 1/2 bosonic fractional phase in this one-dimensional system. Now, if we want to go to more interesting, or not more interesting, but more complicated phases, higher fractions, n equal 1/3, 1/4, 1/5, what we do is we do a nice Jorno-Wigner mapping. So we take every electron or every particle, if it's a boson, every atom, every electron in our ladder, and we take with it the length of its interaction, of our strong interaction, and we can map it using a Jordan-Wigner transformation to a system of non-interacting fermions with a smaller length. And using this mapping, we can in fact calculate all the parameters and scale dimensions of the fractional phases. And we can determine that indeed we can access any even or 1/odd fermionic or bosonic phase that we would like just by taking a long enough interaction. So now we need our interaction not to be just on site. So if we want to achieve, for example, the n equal 1/3, it's enough to take next to nearest neighbor interaction. If we want to get the n equal 1/5, we need next to next nearest neighbor interaction, and so on. And so the important thing that I want you to note here is that we can access any fractional, any simple 1/even or 1/odd fractional phase just by taking strong interacting ladder. So now that we've seen how to generate those phases, the question is, what can be measured? So if we are talking about fermionic systems, specifically about electronic systems, then what we can do is we try to replicate the stuff that can be done for the two-dimensional fractional quantum Hall effect. Namely, we can try connecting them to non-interacting leads and do transport measurements, try to measure the conductance and short noise Fanu factor. And what we see that's very similar to the properties of the two-dimensional fractional quantum Hall effect, we get similar properties of our one-dimensional fractional ladders, where we get a universal fractional value of both the conductors and Fanu factor. But this can only be done if we are talking about electronic systems that are connected to non-interacting leads. What if we have a bosonic system, say a cold atom system, and we can't connect it to non-interacting leads, and we still want to make a measurement that would tell us, that would signify with this signature of the fact that we are within a fractional phase. So what we're suggesting is to look at the chiral currents in dot sample. So just to give you a brief review of what are the chiral currents, so I'm going to talk about chiral currents in two-dimensional fractional quantum Hall effect. So because the gap is bulk, what we have is an edge states, and what can we realize is that the edge state in a fractional quantum Hall effect is in fact a chiral current. And this chiral current is just proportional to the velocity of the edge and the density of the charges along the edge of the fractional quantum Hall droplet. But because the electrons in the fractional quantum Hall phase are entangled with the electromagnetic potential, what we see, and we can find this expression in many textbooks of the fractional quantum Hall effect, is the fact that the current along the edges is proportional not only to the density of electrons, but also to the electromagnetic potential along the edges of our sample. So this is a very standard expression, but what I want you to notice is that if we simply derive it, we can get a relation of that current. Okay, we can get a relation of that current that tells us that the current itself is constant along contours of varying both the electron density and the electromagnetic potential while staying in the same filling factor. So if you would look at a map of the varying current, of variations of the current by changing the density of the electrons and the electromagnetic interaction, we would be able to give us a signature that we are indeed in a fractional state. So just to make it more specific, This is just a simple analysis of non-interacting particles, fermionic particles, in an integer quantum Hall state. And what we see is that indeed around the integer filling factors, we see that if we plot the map of the chiral current as factor of the density and the magnetic field, the chiral current is constant. If you look at the grayscale current, the chiral current is constant next and along the lines that are parallel to those integer phases. And of course, if we would have had an interacting system, we'd expect to get exactly the same result in the two-dimensional fractional states. And so this brings us back to our one-dimensional system. So as I've said, I immediately showed that this result stays the same for our one-dimensional system. So in order to calculate the calculating current and its derivatives, what we do is we realize that the circulating current, or the chiral current, is a persistent current that is related to the derivatives of the Hamiltonian to the flux per plaquette. It's the thermodynamical quantity of our system. And by noticing that, all we need to do is to use a bosonization of the Hamiltonian, which I will not dwell upon. And by simply taking the relevant limit of our operators, we find that the chiral current satisfies exactly the same equation that we've found of the two-dimensional states. 1 minute, okay, so I'll conclude. Exactly the same properties of our two-dimensional states. And we can do it by plotting similar graphs. So if we take the non-interacting one-dimensional ladder, we get a similar behavior, whereby if you look at the current contours, they are parallel to the lines of the exact filling factor. And we'd expect, by doing chiral current measurements that can be made, that once we've had interaction to our ladder, we would find those telltale signs of the n equal 1/3 by looking just at the characteristics and derivatives of the current. So let me conclude. So what I've shown you here are two main results. The first one is the fact that the one-dimensional ladders, by adding interactions, can enable us to access any fractional phase, 1 over even, 1 over odd, fermionic or bosonic fractional quantum Hall phase. And the next thing, that if we want to probe those phases, mainly in a bosonic system, what we can do is we can make chiral current measurements, and the contours of the chiral current would indicate that we are in the fractional phase. And as I said at the beginning, just flash what we're currently doing with the group in Pisa. So Marcello Strinati, we're working with him about finishing numerical DMRG verifications and trying to measure the contours of the chiral current, in fact doing DMRG verifications. Another thing we're looking at with Luca Tadia is the fact that we can generalize our analysis not just to 2-leg ladders, still a quasi-one-dimensional system, let's say 3-leg ladders or 4-leg ladders, adding more ladders to the system and trying to do charge pumping around those ladders and trying to achieve the quantized charge of those systems directly by pumping. And of course, what we would like to do the most is try to convince an experimentalist to study the n equal 1/2 phase in cold atom system that, as I've said before, only requires on-site interactions. Thank you very much.
Question?
If you make it a 3-leg ladder, etc., so what would happen to the densities? Because if it's 2D from bosons, you can get only 1 over even and not 1 over odd. So how does that go as you increase the width?
It stays the same. You can only get the simplest phase that you study here, only 1 over even if you increase the length. You get 1 over even for bosons and 1 over odd for fermions.
Oh, so you're saying 1 over odd, it was just for fermions?
Yeah. All the 1 over odd phases are for fermionic systems, and all the 1 over even phases are for bosonic systems. Yes?
Did you consider case where the bosons are also commensurate with the lattice?
Actually, yes. This is a great question. We've studied possible commensurabilities with the lattice of the bosons, and what we see is that if the bosons are commensurate with the lattice, we can get a charge density waves or a vortex lattice that has been measured by the experiment. But generally, once you avoid those commensurability, once you make sure that you don't specify those commensurability conditions, you can ensure that you'll only get the fractional quantum Hall phase.
Okay, so let the speaker again.
Thank you.